Download this code from codegive.com, link in the description below. Mastering Back Pressure in Reactive Distributed Systems, a comprehensive guide. Back pressure is a critical concept in reactive distributed systems, ensuring robustness, stability, and efficient resource utilization. Without proper back pressure management, systems can easily become overwhelmed, leading to performance degradation, data loss, and even cascading failures. This tutorial will delve deep into back pressure, covering its core principles, different strategies, and practical code examples using popular reactive frameworks like akka and Reactor. 1. What is back pressure? Imagine a pipeline where data flows from a producer to a consumer. If the producer generates data faster than the consumer can process it, a backlog of data starts accumulating. This backlog eventually overwhelms the consumer, leading to resource exhaustion, example memory, CPU, and potential failure. Back pressure is a mechanism that allows the consumer to signal to the producer that it's becoming overwhelmed and needs the producer to slow down the rate at which it's sending data. Essentially, it's a form of flow control that allows the consumer to dictate the pace of data processing. Why is back pressure important in reactive distributed systems? Resource management prevents overloading components with more data than they can handle, avoiding resource exhaustion and ensuring efficient resource utilization. Stability and resilience protects the system from cascading failures. If one component is overloaded, back pressure prevents the overload from propagating to other components. Responsiveness maintains responsiveness by preventing the system from becoming bogged down by excessive backlog. Data integrity prevents data loss by ensuring that all data can be processed within a reasonable time frame. Scalability enables systems to scale gracefully by adapting to varying workloads without crashing. 2. Principles of reactive systems and back pressure. Back pressure is deeply rooted in the principles of reactive systems, as defined by the Reactive Manifesto. Responsive the system responds in a timely manner if at all possible. Back pressure helps maintain responsiveness by preventing overload. Resilient the system stays responsive in the face of failure. Back pressure protects the system from cascading failures caused by overloaded components. Elastic the system stays responsive under varying workload. Back pressure enables the system to adapt to fluctuations in data rates. Message-driven systems establish a boundary between components that isolates failures, enables location transparency, and provides the means to manage resource consumption. Back pressure. Message-driven communication is the foundation for implementing back pressure. Instead of a producer passively pushing data to a consumer, the consumer actively requests data from the producer, controlling the flow. 3. Types of back pressure. Explicit back pressure. The consumer explicitly signals its capacity or request for data to the producer. This is typically achieved through control messages or protocol-level mechanisms. Example: reactive streams request method. Implicit back pressure. The producer monitors the consumer's buffer or processing rate and adjusts its sending rate accordingly. This can be achieved through techniques like rate limiting or queue monitoring. 4. Strategies for implementing back pressure. Drop. Simply drop data that exceeds the consumer's capacity. This is the simplest approach but results in data loss. Acceptable for non-critical data or when data loss can be tolerated. Buffer. Temporarily store data in a buffer or queue until the consumer is ready to process it. Requires careful sizing to avoid memory exhaustion. Suitable when bursts of data are expected. Rate limiting. Restrict the rate at which the producer sends data, ensuring that the consumer is not overwhelmed. Effective for controlling overall flow. Throttle similar to rate limiting, but with more fine-grained control over the rate of data transmission. Demand shaping a more advanced technique where the producer dynamically adjusts its production rate based on the consumer's demand. Requires feedback mechanisms and sophisticated algorithms. Fusion combining multiple processing steps or operators into a single unit to reduce the overhead and latency involved in back pressure signaling. This is often done within a single reactive framework. 5. Back pressure in reactive streams. Reactive streams is a standard for asynchronous stream processing with non-blocking back pressure. It defines 4 key interfaces. Publisher represents the data source, the producer. Subscriber represents the data consumer. Subscription represents the connection between a publisher and a subscriber. It contains the request, long N, method that the subscriber uses to signal its demand to the publisher. Processor represents a processing stage that acts as both a publisher and a subscriber. Key mechanisms in reactive streams request, long N, the subscriber calls this method on the subscription to signal its demand for N data elements. On next, T item, the publisher calls this method to send data to the subscriber. On error, throwable T, the publisher calls this method to signal an error. On complete, the publisher calls this method to signal that no more data will be sent. Cancel, the subscriber calls this method to terminate the subscription. 6. Code examples, akka and reactor. Let's look at how back pressure is implemented in 2 popular reactive frameworks, akka and reactor. Akka streams. Akka streams provides a powerful and flexible API for building reactive stream processing pipelines. It uses the reactive streams standard under the hood. Explanation source, 1 to 1000, creates a source that emits integers from 1 to 1000. This simulates a fast producer. Sync. For each int number equals. Creates a sync that consumes integers and simulates slow processing by sleeping for 10 milliseconds. This simulates a slow consumer. Numbers.to, slow processor, .run, connects the source to the sync and starts the stream processing. Akka streams implicitly handles back pressure. The source will only emit data as fast as the sync can consume it. Flow int.buffer, 10, overflow strategy. Drop head, this line demonstrates an explicit buffer. It buffers the incoming data with a maximum size of 10 elements. If the buffer becomes full, the overflow strategy. Drop head strategy will drop the oldest elements to make space for new ones. Akka provides various overflow strategies such as drop new, drop buffer, back pressure, or fail. Key Akka streams back pressure concepts graph DSL Akka streams uses a graph DSL to define complex stream processing pipelines. This allows you to connect multiple sources, sinks, and flows in a flexible and modular way. Flow represents a transformation stage in the stream processing pipeline. You can use flow to filter, map, aggregate, and perform other operations on the data stream. Buffer operator flow.buffer allows you to explicitly add a buffer with a specific overflow strategy. Overflow strategy specifies how to handle the overflow of a buffer. Options include drop head, drop tail, drop buffer, drop new, fail, and back pressure. The back pressure strategy propagates the back pressure signal further upstream. B. Reactor, Project Reactor. Reactor is a fully reactive framework for building non-blocking, asynchronous, and event-driven applications. It provides a rich set of operators for handling back pressure. Explanation asterisk. Asterisk flux.range, 1000, asterisk creates a flux that emits integers from 1 to 1000, simulating a fast producer. Asterisk delay elements, duration. Of millis, 10, asterisk simulates slow processing by delaying each element by 10 milliseconds. This represents a slow consumer. Asterisk subscribe, asterisk subscribes to the flux and defines the actions to be performed for each element, error, and completion signal. Asterisk publish on, schedulers. Bounded elastic, asterisk this is crucial for demonstration. It moves the consumption onto a dedicated thread pool, bounded elastic. Without this, the main thread would be blocked by the delay element's call, and back pressure wouldn't be as visible because everything would be running sequentially. Reactor back pressure operators asterisk. Asterisk on back pressure buffer, asterisk buffers elements until the subscriber is ready to consume them. You can specify the buffer size and a strategy for handling overflow, example dropping the oldest element using on back pressure buffer, 10, o-system.out.println, dropped, plus o. Asterisk on back pressure drop, asterisk drops elements when the subscriber is unable to keep up. You can optionally provide a consumer to handle the dropped elements, example log them. Asterisk on back pressure latest, asterisk keeps only the most recent element when the subscriber is unable to keep up, discarding older elements. Asterisk request, asterisk subscribers can manually control demand by requesting a specific number of elements. Key reactor back pressure concepts asterisk. Asterisk flux asterisk represents an asynchronous sequence of 0n items, like observable in RxJava. Asterisk mono asterisk represents an asynchronous sequence of 0-1 items. Asterisk schedulers asterisk provides different thread pools for executing reactive operations. Schedulers. Bounded elastic, is suitable for IO-bound operations. Schedulers. Parallel, is suitable for CPU-bound operations. Asterisk publish on, and subscribe on, asterisk control which thread the publisher and subscriber run on, respectively. These are essential for asynchronous processing and effective back pressure. 7. Back pressure in distributed systems, beyond single process. When dealing with distributed systems, back pressure becomes more complex, as it involves communication between different processes, potentially over a network. Challenges asterisk. Asterisk network latency can delay back pressure signals, making it harder to react quickly to overload situations. Asterisk fault tolerance network failures or component crashes can disrupt back pressure mechanisms. Asterisk complexity implementing back pressure across multiple processes requires careful coordination and communication. Strategies for distributed back pressure end-to-end back pressure implement back pressure across the entire system, from the initial data source to the final consumer. This requires a standardized protocol for back pressure signaling. Local back pressure implement back pressure within each component or process. This provides a first line of defense against overload. Rate limiting at the edge apply rate limiting at the entry points of the system, example API gateways, to prevent excessive requests from overwhelming downstream components. Circuit breakers use circuit breakers to detect and prevent cascading failures. When a component is overloaded, the circuit breaker can trip, temporarily preventing requests from being sent to that component. Asterisk monitoring and alerting. Asterisk monitor system performance metrics, example CPU usage, memory usage, queue lengths, and set up alerts to detect potential overload situations. Example, distributed back pressure with message queues, Kafka, RabbitMQ. Message queues like Kafka and RabbitMQ provide built-in mechanisms for back pressure. Kafka uses a pull-based model where consumers request data from brokers. Consumers can control the rate at which they consume data, providing back pressure to the brokers. The brokers also have limits on the amount of data they can buffer, further limiting the producer's rate. RabbitMQ supports various QoS, quality of service, settings that allow consumers to limit the number of unacknowledged messages they have in flight. This provides back pressure to the publisher. Example scenario, conceptual. One web application, producer generates events and publishes them to a Kafka topic. Two Kafka brokers store the events in the topic. 3 Data processing service, consumer subscribes to the Kafka topic and processes the events. If the data processing service becomes overloaded, 1. It will reduce its consumption rate. The service will fetch fewer messages from Kafka per poll. 2. Kafka will buffer the messages. Kafka brokers will buffer the messages that are not consumed by the service, up to a configured limit. 3. Web application might experience slower write performance. If Kafka's buffer is full, the web application's write operations to Kafka may be throttled, providing back pressure to the producer. 8. Best practices for back pressure. Design with back pressure in mind. Consider back pressure from the initial design phase of your system. Use reactive frameworks. Leverage reactive frameworks like akka and reactor that provide built-in support for back pressure. Monitor key metrics. Monitor system performance metrics to detect potential overload situations. Test back pressure scenarios. Thoroughly test your system under different load conditions to ensure that back pressure is working correctly. Choose the right strategy. Select the appropriate back pressure strategy based on the specific requirements of your application. Don't ignore errors. Handle errors gracefully and propagate error signals appropriately. Document your back pressure strategy. Clearly document your back pressure strategy so that others can understand how the system is designed to handle overload. 9. Conclusion. Back pressure is a fundamental concept for building robust, scalable, and resilient reactive distributed systems. By understanding the principles of back pressure and utilizing the appropriate strategies and frameworks, you can create systems that can handle varying workloads and gracefully recover from overload situations. Remember to design with back pressure in mind, monitor your system performance, and thoroughly test your implementation to ensure that it is working correctly. Mastering back pressure is essential for building reliable and performant reactive applications in the cloud and beyond.